All right, guys. Good morning. So this is week 5. Couple of announcements is first is about the quiz. This is the quiz. This quiz is due 11 a.m. today. So if you haven't done it, if you haven't done this quiz, please do so before 11. Right. And I note that some of you guys have problems doing the quizzes, and I send you guys an email, but I don't know whether you read my emails or not. I don't know. The quizzes this year are very similar to the quizzes from last year. So these are the quizzes and the solutions. These are the quizzes and the solutions from 2021, right? And for example, if you look at quiz number 4, this is last year's quiz number 4, which is very similar to this year's quiz number 4, right? So if you can practice on this, guys, if you have issues doing the quizzes, try to practice on the quizzes last year and see if you can get the correct answers, because the solutions are there. So for example, this is the solution for last year's quiz number 4, right? Okay, I think that will really help you, because I mean these are not like quizzes you can do it in a minute or 5 minutes. It takes a while to do these quizzes, right? So you need to spend some time, to do these quizzes. So I think a good way to do this is to practice on the last year's quizzes, which are very similar to the ones this year, right? All right, the second announcement is about the tutorial. If you haven't been to the computer lab sessions this week, there is one this afternoon at 2 o'clock. So please do go to the one at 2 o'clock today in the ATB computer cluster. Okay, so it's important that you do attend the tutorial sessions. I note that the attendance has been going down in the tutorials as well as lectures, which is not good, right? Okay. All right. So those are the two announcements. Unless you have something you want to talk about. All right. This week I asked you guys to watch this video. So this is the video. This is the video I asked you guys to watch, right? And basically it contains 10 examples on point estimation. These are the 10 examples. So the example 1 is on this, example 2 on this, this is example 3, example 4, and so on up to example 10. So what I'm going to do today is to do more examples in addition to the 10 examples. Remember last week I talked about point estimation, right? So this week we're going to do examples on point estimation, and there are 10 of these examples. There are 10 of these examples. I ask you to go through this. Now before I start, can I ask you, had you guys been to these 10 examples or not? I mean, had you guys watched the 10 examples? Is there a particular example that you had difficulties understanding, or examples? Feel free to give a shout, guys. Like, is there an example out of these 10 that you would like me to go over? Hello? Can you hear me? Is it? Is there like any particular example you'd like me to go over again? Are you okay with this example 9? Okay, let me go through it one at a time. So let me start with example 1. Let me start with example. Are you guys okay with example 1? Yes or no? Okay. Example 2, are you okay? Are you able to understand? Example 3, you guys okay? Just say no, yes or no, guys, please. I'm trying to help you. Are you okay with example 3, guys? Yeah? Example 4. Feel free to say no, I'm happy to go over. Example 4, okay? Example 5, no? You have problems? Okay, all right, let me go through example 5. So as you can see, there are, so this is, example 5. So you have two data points from a uniform theta plus 1, and we have the maximum or the larger of the two data points as an estimator for theta. Right? And the question is to find the bias. Right? So we have theta hat. Theta hat is the estimate for theta and is defined to be the larger of the two data points. Right? If you're just coming in, I'm doing example 5 from the video, right? So in order to find the bias of it, remember the definition of bias is the expectation of the estimator minus the parameter that you're trying to estimate. Yeah? Okay? Now, this is the expectation of right now, in order to find the expectation, you can't take the expectation inside the max. That's not allowed to. That's not an valid operation, right? You can't take the expectation inside the maximum, right? So what you need to do is to work out the distribution of this guy here. Let me call this Z, but you can call it any other name, right? You don't need to call it Z. You can call it W, A, B, C, any other name, right? Now what I'm going to do is I'm going to work out the distribution of Z and then use that to find the expectation of Z, right? So the first thing I'm going to do is to find the CDF of Z. Remember, the CDF is defined as the probability, okay? And this is the probability that the maximum right. Now, this is where some of you are struggling, I note, that if the maximum of two numbers is less than something, what does it imply? It implies what? If the larger of two data points is less than something, it implies that both data points has to be less, right? You follow that or not? So if the larger of the two is less than or equal to Z, then x1 has to be less than or equal to Z, and x2 has to be less than or equal to Z. I mean, it's simple logic. Yeah? Yeah? Okay? Now, the next step, I'm going to use the fact that x1 and x2 are IID, which is given in the question. I mean, if you read, we are saying IID, which includes independence, right? So using independence, you can write this as the probability that right now what you have here is the CDF of x1. What you have here is the CDF of x2. Now we are assuming that x1 and x2 are uniform theta plus 1. So you should know from probability 1, you should know what the CDF of a uniform is, right? If you don't remember, I can show you just a minute. If you don't remember what the CDF is, you go into this and click on this link here. You should go to the uniform distribution here. No, it doesn't give it only gives the PDF, but I'm sure you know what the CDF is, right? The CDF is simply Z minus A divided by B minus A. So in this case, Z minus theta divided by theta plus 1 minus theta. Yeah. Okay, so this will be, you should take the product of these two. This is what you get. Okay. So that's the CDF of Z. Now what we need, in order to find the expectation, we need the PDF, not the CDF, right? So the PDF of Z is simply the derivative of this with respect to Z, which is 2 times Z minus theta. This is the derivative of this, yeah? Okay, now we return to this. I'm going to return to this. I'm going to find the expectation. So let me put this in a box, kind of, so that. So you find the expectation of Z minus theta. Now remember, for a continuous distribution, the expectation is integral, right? Okay, so this is the integral from theta to theta plus 1 times Z multiplied by 2 dz minus theta. Okay. So if you do the integration, you get Z cubed by 3 minus theta Z squared by 2. Take the limits from theta to theta plus 1. I'm sure you guys are all experts in integration. I'm not going to spend my time doing the integration, but this, you will get something which is not equal to 0, right? Basically, I'm sure you know how to do integration, right? So you'll get something that is not equal to 0, and hence theta hat is a biased estimator of theta. Right? Is that clear now, guys? Okay, I'm just going through, if you just came in, I'm just going through the 10 examples I asked you guys to watch. So this was example 5. Sorry, what's happening? So what I just did was example 5. Yeah, this was example 5, right? Any other questions on example 5 before I go to the next one? Are you guys clear about example 5? Yes, no? Just feel free to say no if it is. Right, now let's go to example 6. Are you okay with this? Yes, no? Okay. Example 7. Example 7, are you okay? Yes or no? Please. No? You have problems? Which part do you have problems, sir? Can you explain? This is a long example, but if you can tell me like why exactly you had problems, it would be helpful for me. Can you tell me, guys, why you had problems in example 7?
The crucial step is the step from this line to this line. I don't know if you can see the crucial step is the line from this to this. And what I have used is a property of a chi-squared variable, right? And let me go back to the website and show you what I have used. Remember, we talked about the chi-square distribution a while ago, right? This is the stuff on the chi-square distribution. Now, one of the properties I gave you, I don't know whether you recall, is this one here, number 6. Property number 6 says that if you have IID normal, then this must have a chi-square distribution with n degree of freedom. Right, so that's what I have used. That's what I have used in this step. From this line to the next line, I have used property number 6 of chi-squared. Does it make sense or no? Hello guys, talk to me. Yeah. Okay, let's go to the next one. Example, are you okay with example 8 or no? Feel free to say no. Are you guys, anybody not okay? Example 9. This is example 9. Okay or not? Hello guys, you sure? What about example 10? What about example 10? Are you okay with this? Anybody who has problems following example 10? You sure guys? I'm doing so many examples because I want you to get a feeling for this bias and MSc stuff, because you will get questions on bias and MSc in the final exam in May or June of this year. So it's important that you have a good feeling for these kind of questions, right? So are you okay with example 10, guys, or not? Yes or no? Anybody with no, feel free to say so. All right. Okay. So these are the 10. If you haven't watched these 10 examples, please go back. Please admit. I know the video is long. It's a long video, I know, but you may not be able to watch it all at once. But you can watch part at a time and try to see if you can understand all 10 examples. And obviously, if you can't, then feel free to contact me 24/7. Yeah? Okay, guys, so what I'm going to do in the rest of the time today is try to do more examples. So let me start with, this is example number 11. So, example 11, so suppose all right, so here you have x, just a single data point, which has the Bernoulli distribution with parameter p,
and the estimate for P is taken to be X itself, and we want to find the bias and the MSC of X. So let's try to find the bias first. So the bias of X, as you know, is the expectation minus P. Now what's the expectation of a Bernoulli? I don't know whether you recall this or not. If you don't, let me show you where it is. You should go up to the top, click on this link. For the Bernoulli distribution, which is this one here, this is the Bernoulli distribution. The expected value is equal to P. So this is P minus P, which is 0. So that means X right. The MSC, using a property that I mentioned in the last review session on Friday last week, is the variance of X plus the square of the bias of X. So this is the variance of X plus 0. Now variance of X, once again, if you look here, is P times 1 minus P. All right, so this is your MSC, or the mean squared error, and this is the bias. All right, so that's an easy example. Now let's look at, are you guys okay with this? Any? Yeah, okay. Next example, example 12. Example 12 is this. Suppose right? So in this case, we have a random sample, not just one data point. We have n data points, assumed to be IID Bernoulli. So we got X bar, which is the sample mean, as the estimator for P. We want to find the bias and the MSC. So let's start with the bias first. So the bias of X bar is right, take the expectation inside, you get 1 over n times the sum of the expectation of xi minus p. Now we know from here that the expected value for a Bernoulli is p, right? So I know this is too easy for some of you, but I mean, the purpose of doing this is to give you enough practice so that you don't have problems. Like the next two quizzes, quiz number 5 and quiz number 6, are on point estimation. So I hope you don't have problems with those, because we have done enough examples on this kind of stuff. So I hope you're okay with the next two quizzes, right? So this is going to be, the sum of a constant is n times the constant, and this is clearly 0. So what this means is that X bar is unbiased for P. The next part is to find the MSC of X bar, which from a property that I proved last Friday is the variance of X bar plus the square of the bias. Right, the bias we know is 0, so this is simply the variance of this guy here. Plus 0. Now, if you take the variance inside, remember when you pull a constant outside of the variance, you need to square it. So when you pull n outside, it becomes n squared times the sum of the variance of xi. Now, if you look at the side screen, you will see that the variance of a Bernoulli is p times 1 minus p. Right? So this guy here is the sum of p times 1 minus p. Now, this is a constant with respect to I. So this is 1 over n squared multiplied by n p 1 minus p, which is p 1 minus p divided by n, and which approaches 0 as n approaches infinity. So hence, so what this implies is that X bar is also consistent. It's a consistent estimator for P. So this estimator has the two good properties of an estimator, that is unbiased and is also consistent, right? Okay, guys. Right. So these are easy examples. I will do something maybe a little bit more difficult. Let me see. This is example 13. All right, here we are. So this is a little bit more involved. Now suppose you have two data points. Suppose right, so here you have two data points from an exponential distribution with parameter 1 over lambda. We have this as an estimate for lambda. So this is 4 divided by pi times the square root of x1, x2. The question is to find the bias and the MSC. So let's see how we can find the bias first. So the bias of lambda hat is the expectation of lambda hat minus lambda. Okay? So this is the expectation of 4 divided by pi times the square root of x1, x2 minus lambda. Yeah? Now 4 divided by pi is a constant, so you can pull it outside. Okay. Now here you have two variables, x1 and x2, that are independent variables. Now what do you know about the product? If you have a product of two independent variables, what is the expectation? I mean, this is something you should have learned in probability 1, that if you have two variables that are independent, then the expectation of the product is what? You remember or what? Come on guys, talk to me. This you can write as what? This you can write as because of independence, you can write the expectation of the square root of x1, x2 as the expectation of the square root of x1 times the expectation of the square root of x2, right? Now what we need to find is these two guys here, okay? We need to find this guy, we need to find this guy, right? So let's see how we can do it, right? So to find if, suppose if x is exponential with parameter 1 over lambda, then the expected value of the square root of x is equal to the integral from 0 to infinity of square root of x 1 over lambda right? So I'm going to put this in a box away from this. Right, now I'm sure all of you know integration better than I do, I guess. Now how would you integrate this, guys? How would you do this integration? You can pull out the 1 over lambda outside. So you have this, yeah? All right, and next I'm gonna make a substitution. I'm gonna say set y equal to x divided by lambda. So x is lambda y and dx is lambda dy. So let me put this in another box, smaller one. Yeah. Now under this substitution, this integral here will become, the lambda will cancel, so it will become square root of lambda times Are you guys with me or lost? So what I have done is to make this substitution inside the integrand here. So you get the lambda here will cancel with this lambda here. You get a square root of lambda because of the x, right? Now, this guy here is the gamma function at 3 over 2. I think I talked about the gamma function. If you don't know what a gamma function is, I suggest it's in the course website. So if you go to the top of this website, you will see there's a video about the gamma function. There's a video about the gamma function which you can watch, right? It tells you everything about gamma function that you need to know, right? Okay? So apparently the gamma function at 3 over 2, you can work it out using the properties that are given here. You can work it out to be I'm not going to go through them, but you can work it out to be square root of pi divided by 2. That's using the properties on the screen, on the two screens here, right? You can work out gamma at 3 over 2 as root pi divided by 2, right? So what I'm saying is that what I'm saying is that the expectation of the square root of x is equal to square root of lambda times pi divided by 2. All right, now going back to this guy here, let me bring it down slowly. So what we have is 4 divided by pi times yeah, you follow me? Guys, so what I have replaced, there are two expectations. There's expectation of the square root of x1 and the expectation of square root of x2. So I have replaced both by this guy here, right? Now, you should simplify this guy. You will get this to be 0, right? So what it implies is that lambda hat is unbiased. Right? Are you guys with me or not? Any questions so far? Any questions? Are you sure? All right. So do you understand why the bias is 0? Okay. All right. The next thing we need to find is the MSc, right? So to find the MSc of lambda hat, I'm going to use the property I proved last Friday, which says okay, this. Now we know that the bias is 0, so this is simply the variance of 4 divided by pi times the square root yeah. Now this is going to be, you should take the 4 over pi outside, it's going to be 16 divided by pi squared times the variance of square root of x1, x2. Right? Now, I'm sure you know that, you know the formula that expectation, sorry, what am I saying? You know that this is the formula for the, you should have a variable z, right? I'm sure you know this formula. The variance of z is equal to this minus this. So I'm going to use that. So this is going to be the expected value of x1, x2 minus the expected value of the square root okay. Are you guys with me? Right? Now, we know this guy here. We already worked out what this guy is equal to, right? So, and by independence, you can write this as this, and you can write All right? Yeah? You guys with me? Now, what's the expected value of x1 let me show you again. You should go to this link here. The expected value of an exponential random variable with parameter lambda is 1 over lambda. Now, but we have 1 over lambda, so this will be, you see, our exponential is with parameter 1 over lambda, not lambda. All right, so the expected value will be lambda times lambda. And this guy we already worked out earlier is I hope you are following me. Okay. So this will become 16 pi squared lambda squared minus lambda squared. Then you have pi squared. Then in the bottom you have 416. All right, so this is going to be lambda squared taken out. Then you have 16 over pi squared minus 1. So this is the mean squared error, unless I made a mistake. I think it's correct. So this is the MSc for lambda hat, and the bias is 0. All right? Are you guys with me or lost? If you're lost, please let me know. Are you okay? I mean, I will scan this and put this on the course webpage, so don't worry if you can't. Don't worry if you are unable to copy, right? All right. Maybe we have time for another example. So at least I will write it down. Maybe you can do it at home. I will write down this example. Are you guys okay with this, by the way, again? Or anybody who did not follow this, let me know. You guys okay? You sure? Okay. Right. So example 14. Let me at least write it down. So perhaps you could try this by yourself. Right? So you have two data points. The expectation of the first and the variance are 2 theta and 4. For the second, the mean and the variance are theta and 2. And you've got two estimators, theta 1 hat and theta 2 hat. The question is, which of the estimate is better and why? So what you need to do is to find to find the bias of the two estimators and find the MSc of the two estimators And depending on the answers that you get, you can decide which estimator is better. Right? Remember, the estimator that has smaller MSC is the better, and the best estimator is the one that has zero bias. Right? So you can see immediately, if I have time, let me try to finish the bias. The bias is the expectation minus theta, right? So the expected value of x divided by 4 plus y divided by 2 minus theta. Now, if you take the expectation inside, you get this minus theta. The expectation of x we know is 2 theta, and the expectation of y we know is theta. So this is clearly 0. So the bias of the first estimator is 0. And the bias of the second estimator is the expectation of theta 2 hat minus theta, which is the expectation of x minus y minus theta, which is the expectation of x minus the expectation of y minus theta. The expectation of x is 2 theta. The expectation of y is theta. So once again, the bias of the two estimators are both equal to 0. So you can say that in terms of bias, both are good, are equally good, right? So what you need to do now is to find the MSC of the two estimators and choose the one that has the smaller MSC, right? I don't know if I have the time, but let me see if I can finish it. Just be patient with me, guys. So the MSC of theta 1 hat is simply equal to the variance of theta 1 hat because the bias is 0. And this is the variance of x divided by 4 plus y divided by 2, which is 1 over 16 times the variance of x plus quarter times the variance of y. Now we know that the variance of x is 4, and we know that the variance of y is 2, right? So if you work this out, this is quarter plus a half, so this is 3 over 4, right? I might check my math, I wouldn't get it wrong. Now similarly, the MSC of this guy, which is the variance of this one, which is the variance of x minus y, right? And variance of x minus y, you should take the variance inside. This is variance of x plus the variance of y. Now variance of x is given as 4, variance of y is given as 2, so this is 6. So clearly, theta 1 hat is the better. Is the better estimator, right? Because it has smaller, remember, the better estimator is the one with the smaller MSC. So in this case, theta 1 hat has MSC equal to 3/4, and theta 2 hat has MSC equal to 6. So clearly, theta 1 hat should be preferred, okay? All right, guys, so once again, if you haven't been to any of the lab sessions this week, please come to the one today or this afternoon at 2 p.m., right? Okay. See you guys. Have a great weekend. Yes, what's up?
For the last example, why did you do 4 plus 2? It should be
No, no, it's plus. When you take the variance, it's plus.
but it's variance of x minus y. It becomes plus.
Yes. Hello, sir. How are you?
Good. I don't understand how you got root pi by 2 for gamma 3 over 2.
This one. You mean from this to this?
From gamma root. Gamma
That's why
3 over 2
you need to look at my video on gamma function. There's a video on gamma function in the course website. Look at it. It explains how to get from this to this.
Yeah.
Yeah, just look at the video. How are you, sir?
I'd just like to ask, so when you compare between two estimators,
Yeah.
you look at the bias and the MSE.
Yeah.
But so in the last example, you could clearly see that theta 1 is the better estimator.
Yeah.
But
Yeah.
what if like there are cases when there are two estimators, one of them has the
Yeah,
has the better bias? and
yeah,
the other
I see what you're saying. Yeah, in that case, you just need to say that in terms of bias, say theta 1 is better. In terms of MSC, theta 2 is better. Yeah, you have to say in your answer like that. Yeah, because sometimes, as you say, sometimes there can be conflicting results depending on bias or MSC, right? So you have to say, like, in terms of bias, this is the better estimator, and in terms of MSC, this is the better estimator. Yeah. Yeah, pleasure. Thank you. Pleasure, man. Hi, you have a question? Yeah. That's because that's the formula for the variance of uniform distribution. There's a formula. You should look at the link I showed you in the common distributions. There's a link on the course website. It gives the formula for the uniform is b minus a squared divided by 12. You remember that formula? It's in the link I showed you earlier. The link for common probability distributions. Yeah, you should look at the link. You'll see. I see.